Just a quick question. Can you think about derivatives, the rules? Can you add derivatives together? Like if you have x squared minus 7, or x squared plus 7x, can you find the derivative of x squared?
Yes.
And then can you add it to the derivative of 7?
Yes.
Okay, yes, you can. Can you subtract?
Mm-hmm.
Okay, what about multiplication in derivatives? You need a special rule, right? It's not just like just multiply and you're all set. What rule did we need? Great. How about antiderivatives? Can you add antiderivatives? Yes. Can you subtract? Can you multiply? Which was one of the questions on the test to see if you understood that you could not multiply. I think it was like, can you multiply to get 14 or something like that? So like the antiderivative by itself was 2 and the other antiderivative was 7. So can you just multiply them to get 14? And a lot of you thought that you could. There is no straight multiplication of antiderivatives. It's not a property. So you need a special rule. Just like in derivatives, you need a special rule called the product rule to be able to do that. In antiderivatives, you need special strategies as well. So we're going to learn a couple different strategies that will allow us to do the antiderivatives of things that are multiplied. Instead of just doing them separately, which is not correct, we need a couple different strategies. The first one is the strategy of what's called U substitution. So what I'm going to do is show you that, recognize when this is beneficial and it helps, would it be helpful to you? And so then we'll just tackle it. Okay, here's an example where U substitution is beneficial but not totally necessary. This is not a product. Okay, this is just simply x minus 4 to the third. You could do this antiderivative multiple ways. One way would be to superfoil it all out. Okay, you could take x minus 4 and multiply it by x minus 4 and multiply it by x minus 4, FOIL the whole thing out, and then do each little individual, because then it would just become a bunch of addition and subtraction. And then you could do the antiderivative that way. You also, in this particular case, can raise the power by 1 and divide by the new power. That is dangerous, however, because it only works in this case, and it would not work if the question was like this. Whoops. Okay, it does work for the left one, it doesn't work for the right one. And so it's dangerous to get into that habit of thinking, oh, I'll just add 1 and divide by the new power. Do you any idea of why it works for one of them and not for the other? What do you think?
Would it be because the coefficient and the chain rule?
Okay, definitely has to do with the chain rule, for sure, 100%. The first one, the chain rule on x minus 4 is 1. So if you don't remember it, no big deal, because it's just 1 and that's not going to hurt you. But the other one, the coefficient, the chain rule, would be what number? 2. And so if you forget it, then then you're going to have the wrong, especially in a multiple choice, that's going to cost you. So I always recommend something called U substitution for this because it will protect you from forgetting the chain rule and it will protect you from making a dumb mistake later. U substitution is better. All right, so I'm going to show you U substitution for this one, even though there are multiple other ways you can do it. U substitution is where you take something that is in the parentheses, so in this case, x minus 4, and simply replace it with the letter U. All right, so that's what we're going to do. We identify what is in the parentheses, x minus 4, and we replace that with the letter U. At the same time, we're going to replace dx as well. Let me show you how to replace dx. dx is where you apply the derivative to what you chose, that you indicated your substitution was. Let's do the derivative. What is the derivative of x minus 4? 1. How do I write the derivative of u? Say that again?
Du.
Not just du, that's called a differential of u. How do I write the derivative of u? Not dy, there's no y's in this problem. Du dx, this is respect to the letter x. So that is the derivative, that's called a derivative. du is the differential part, which means it's just the numerator. So how do I get that numerator by itself? How do I separate du from dx? Multiply by dx. So I can multiply this side by dx, and I multiply this side by dx. So what I end up with is that du is equal to 1 dx, or just plain dx. It's a very simple, straightforward, basic question. I'm just showing you the method so that we can do more complicated ones. This is sort of like, I talk about pre-write. This is the pre-work that you do. You go back to your integral and you change what was in the parentheses, which was x minus 4. We are going to change x minus 4 into u. Still has the cube on it. We are going to change dx into du. So I end up with the integral is now u cubed du. I can do an antiderivative on that. The antiderivative on u cubed du is 1/4 of u to the 4th plus the constant c. Again, this is a very easy example, very basic. Then at the end, you change u back to what it represented, which is the parentheses, x minus 4 to the 4th plus the constant of c. I just want to reiterate, I didn't need a u substitution in this one. I'm just using it as an example to show you. And the reason I don't necessarily need the u is because the derivative was 1. Any other time where the derivative is not 1, you have to use the u substitution. Yeah?
So that 1 equals the dx is the derivative of whatever is like in here?
Mm-hmm.
Okay.
Mm-hmm. All right, any other questions about that one? Okay, I was going to show you like the foiled out way to do it, just to hopefully sell you on that u substitution is the better way to do it, but we're going to skip FOIL. It's just too long. I don't want to feel like doing it today. All right. This strategy, rule of thumb number 1, if there are parentheses in your original problem, u substitution is almost always the best way to go, most easily. Is it the only way to go? No. It's usually the easiest way to go. All right, you see parentheses. All right, do you see parentheses? Great. All right, is u substitution the only way to do this? And the answer is no. Is it, I'm going to arguably the best way to do it, and I'm going to hopefully convince you that it would be yes. All right, so we are going to claim the thing that's in parentheses as our u substitution. So 5x minus 7 is what we are going to replace with the single letter of u. On that, we're going to check what the derivatives are. So on the 5x minus 7 side, the derivative is simply the number 5. On the u side, the derivative is du over dx. Then I manipulate those du over dx by separating the differentials. So I multiply both sides by dx. So basically 5 dx equals du. And I need dx to be alone. So dx would be 1/5 of du. So you need a couple things to be alone. You need the u to be alone that you start with, and you need the dx to be alone so that you can go back to your original equation and make the substitutions that you need. So that's all the pre-work that you do somewhere on the side. You go back, equal signs. Okay, we're getting good about our equal signs. We are changing the inside. The inside is changing to u. The dx is changing to 1/5 of du. So in other words, your original equation had variables that were all x's. Your replacement equation should be variables that are all u's. There should never be a mixture of the variables, right? If you end up with a mixture of some u's and some x's, then you did something wrong. Yeah, William.
Would it be wrong to write du over 5? Or?
Not wrong to write du over 5. I typically write the 1/5 because I like to pull it out to the front. Okay, up to you though. Then I can do my antiderivative. So the 1/5 just sits out in the front. The antiderivative of cosine is sine of u plus c. Yeah. The antiderivative, the derivative of cosine is, yeah. And then my last step would be to revert this problem back to what the parentheses stood for. And so my final answer would be the 1/5 of the sine of the quantity 5x minus 7 plus c. Okay, again, not the only way, but when we get to products, this still was not a product. When we get to products, it is the only way. Yeah.
So the 1/5 only goes to the first part?
That's a good question. She's asking about distributing this 1/5, right? This 1/5 here. Okay. 1/5 is a constant. If I distribute it to c, which is also a constant, the result will be a constant as well. Okay. It is. You may, if you like to change it to a new letter, you may, just to represent that it's different, but it's still a constant. 1/5 times a constant is still a constant. Okay. All right, any other questions so far? Yeah.
Maybe kind of a random question, but is there a term that is in math for like multiplying something by dx? Like would we use that for substitution?
Like when we're doing it right here and we're multiplying by dx on both sides, like that. The term is like, well, we're just multiplying by the denominator. Here's something similar. If you had 5 equals 3 over x. No. I'll do it the other way around. X over 3. And you wanted to solve for x. You would multiply by the denominator.
I was curious. If
So we just say we're multiplying by the denominator, so we do that, and then x is equal to 15. So in the same way we're doing with the dx, we are multiplying by the denominator, or clearing the denominator. That's another way they'll say.
So like mathematicians just found that as a method that you could use.
So this was definitely a Leibniz thing, that he found that you could separate du and dx, and you could move them out as separate quantities. They weren't like glued together in one thing. Were removable from each other. All right, really good questions. Okay, here we go. Here's another one. U substitution is the best option here because it can be written as parentheses. That is always the question you ask yourself. Could I write this in such a way that it would have parentheses? And if the answer is yes, then it's like U substitution is going to be the way to go. So your first thing would be to pre-write that in parentheses. Anybody want to take a stab at that? How would you pre-write that? Okay, Zach?
3x plus 2 to the negative 1/2.
Yes, 3x plus 2 quantity. There's your parentheses to the negative 1/2 dx. That clearly identifies what should be your u choice. And so we would choose as our u 3x plus 2 as representative of what u is going to be. Then we do our pre-work of finding the derivative on both sides. So 3 on one side, du dx on the other, and then manipulating the pieces of that equation by multiplying by the denominator. So we'll ultimately have dx is 1/3 of du. That pre-work being completed, we can go back to our integral and replace the parentheses with u and replace the dx with 1/3 of du. And now we're in the rhythm. Now we are, okay, I can pull 1/3 out to the front. And I can work on a bracketed antiderivative. So the antiderivative would still have parentheses around u, but now it would be raised to the 2/3 power and then divided by,
1/2.
oh, whoops, I changed it on accident. Thanks. Let's fix that. I had 3 on the brain. How about that? All right, raise it to the 1/2 power, divide it by 1/2, or a better way, instead of dividing by 1/2, we would multiply by the number 2 plus c, which basically means 2/3 parentheses u to the 1/2 plus c. So your constant of 1/3 out in the front, and your new other constant of 2 is a coefficient, then you're going to change it back to 3x plus 2 to the 1/2 plus c. You may continue to write that as a square root if you like, or you may leave it like this with the 1/2 power, doesn't matter. The only thing you can't do is leave a negative exponent. So you may leave a fractional exponent as long as it's positive. You may write it as a square root. Your personal preference, just don't leave a negative. Zach?
Do you not have to distribute 1/3 to the c?
Okay, that's a really good question. Anybody want to tackle his question? Should he distribute the 1/3 to the c? Jackson?
Yeah, but it stays a constant, so we can write it as plus c still, right?
1/3 distributed to the constant c is just a third of that constant c, which is still another constant. So for ease, we just continue to call it. If for your own purposes you want to change that to constant k or constant g or constant, I don't care, z for Zach, it doesn't matter. Yeah.
So does that mean that you have a point like t, or like if f0 equals this, you just plug it in with the 2/3 there and you get the values to spread?
All right, yeah.
So if you're showing work for like on that test or
Mm-hmm.
whatever, do you have to do every single one of those steps?
Okay, that's another good question. All right, right now I'm being intentional about, so did you notice like this time I eliminated one of the steps as I got my dx alone? I don't know if you caught that, like I didn't show that I was multiplying by dx and I didn't show that I was dividing by 3. I kind of made that. So yeah, as we get more fluid with these, you can show fewer steps. Yeah, but like what they are going to look for, do you identify your u? Is that clear? Right? So that at least to identify your u, and then to identify what your dx ends up being. Those are the kind of the non-negotiables. All right, here's your second rule of thumb. So first rule of thumb, if you see parentheses, u substitution is going to be one of the best ways to go. Second rule of thumb, if you see a product or you see a quotient, because a quotient is really just a product in disguise. A quotient is the exact same as a product, right? So I should be able to convince you that, I'll write it here, I guess. This is a quotient, which is really just a product in disguise. What it's the product of? 3 and what? Okay. So every quotient should be written as a product. Every product should be done with u substitution. So those are your 2 rules of thumb so far. Okay, here is a product. So you'll want to do your pre-write to identify this as a product. So my first pre-write would be say, okay, I see this as 6x times parentheses 1 plus x squared to the 1/2 dx. This has got the double whammy. It has parentheses and it's a product. So for sure, u substitution is going to be the way to go. You're going to pick what's in the parentheses. So 1 plus x squared is going to be equal to my u. That's my pre-work. So now I want to do the derivatives here. What is the derivative of 1 plus 2x? I just gave it away. 1 plus x squared. All right, 2x. And then on the other side, we have du dx. I need to work and manipulate that so that dx is alone. Okay, I'm going to clearly work. So I'll show my good steps here. I'm going to multiply by dx on both sides. That's going to give me 2x times dx equals du. That got me du alone, but I don't need du alone. I need dx alone. So dx is going to be 1 over 2x times du. Okay, always work to get the dx alone. Now we go back, so our pre-work is done. We're going to go back to our integral. The only two places we are going to substitute are going to be in the parentheses and the dx. Okay, these are the only, we're going to substitute here and we're going to substitute here. Don't worry about the 6x right now. Trust me, it'll be all right. Okay, we're only going to make those two substitutions. So I'm going to end up with 6x times parentheses u to the half times 1 over 2x times du. Why do we need not worry about that 6x? It's going to reduce with what other term? 1 over 2x. And what will I be left with? 3. That will always happen. It should always happen. You should always be able to reduce so that what variable is the only variable left? A u. That should be it. If you have any x's left, you did something wrong. Something in your process didn't go right. Maybe it was you chose the wrong u at the beginning or you made a derivative mistake, but that's always a checks and balances. Okay, if you have any x's that are left, something's in your process isn't right. So we can simplify to just the number 3 pulled out in front of u to the half du. Every problem is designed in such a way that if you're doing your process right, you'll end up with just a u quantity and no other variable. So then I can go to my antiderivative. So 3 times the antiderivative. U is now going to be to the positive 3/2 times the quotient times the reciprocal 2/3 plus c. Thinking about my distributing, when I distribute the 3 in to the first quantity, I'll be left with the number 2. When I distribute 3 out to my c, it's still going to be a constant. So I will have 2 quantity u to the 3/2 plus c. So my final answer would be to change this back into 2 quantity 1 plus x squared to the 3/2 plus the constant of c. This is how a product works. You can't take the antiderivative individual pieces, but by substituting, one of the pieces disappears. All right, any questions on that? Okay, there you go. This one's already written for you. Should be pretty clear what your u is going to be. So we're going to claim what's in the parentheses, 2x squared, as our u. My derivative will be 4x equals du dx. So then dx ends up to be 1 over 4x du. So you're going to should get pretty fluent in moving your du dx differential terms around and getting that dx by itself. So that's my pre-work. And then we'll go back to my original equation and figure out what I can substitute for. What we're going to substitute for is what we chose in the parentheses and the dx. And for the moment, we're not going to worry about that x because we're going to trust the process. So I'll end up with x times the sine of u and then times the fraction 1 over the 4x times the differential of u. So when we trust the process, we should see that my x terms reduce, leaving me with the constant of 1/4 out in front of the integral of the sine of u du. So everything should work out real smoothly for us. So my antiderivative now is the negative cosine of u plus c. Which means negative 1/4 of the cosine of the quantity, 2x squared plus c. On your test, I could tell that some of you had a hunch that there were ways to do these kind of antiderivatives. And you were trying really hard to do separate antiderivatives, like an antiderivative of the x piece and turning that into an antiderivative, and the antiderivative of the sine piece, and you were trying to do a lot of things. But it was on your test, it was on the calculator part. So on the calculator part, I'm just expecting you to not do any antiderivatives at all. I'm just expecting you to go math 9. Okay, because you didn't know how to do that, yeah.
Negative cosine or is it cosine?
No, we can.
The antiderivative would be negative, yeah. But it wouldn't be uncommon for me to make a mistake, so thank you for checking me on that. All right, so you've got 2 tips on how to choose u right now. U is the thing in the parentheses. So do pre-writes. Okay, U is part of that product. Now, what if there are 2 sets of parentheses? How do you choose which U is the right U? Because that might happen. Okay, how do you choose which one? In these questions, if there's more than one option for U, these problems are designed in such a way that one of them is the derivative of the other. That are always going to set it up that way. In other words, if one of the parentheses of the problem had x cubed in it, one of the other parentheses is going to have 3x squared in it. I just promise that they're being gentle with you. They're setting them all up for you, that they all are like that. So you've got 2 choices. Which one do you think you want to choose? The higher one. Okay, always choose that as your u. Because if you trust the process, when you work out its derivative, it will reduce out the other one. So if you have multiple choices, it's always choose the one that's not the derivative. Choose the one that's the other. So here's an example. Here's a multiplication problem. And if we look at a pre-write on this, we do have a couple different options. We could pre-write this as x squared e to the quantity x cubed. You could think about it that way. There are 2 different quantities of x. What, Jackson?
I put e in the parentheses with it, so I took the derivative of that and it didn't work. So.
But see, that's part of the check. You were working ahead.
I just wanted to work one ahead.
Right. That's the part of the checks and balances. When it doesn't work out, that all that means is the thing you chose for the u at the beginning was not the right thing.
Yep.
Okay. So like, remember the one we did before? It was like sine of this. We didn't choose the sine part. So we're not going to choose the e part as part of our u. We're only going to choose the x cubed part. So we will be choosing x cubed as our u. So 3x squared will be our du dx. So dx turns out to be 1 over 3x squared du. So we're choosing this higher power option, and we're choosing dx. We do not choose the e, just like we did not choose the sine. E is the type of function it is, but it's the x squared part that we want. So then we're not going to worry about this x squared right now. And e will be to the u in parentheses. And then we'll have 1 over 3x squared times du. So our faith in the process should be rewarded at this point, because our faith showed us we needed to choose the higher power. And now the x squared terms reduce. So we're left with 1/3 of e to the u du. So 1/3 was my constant. Then I can work on an antiderivative. So we've done some antiderivatives of sine and cosine. We've done some antiderivatives of powers. Now we need to know our antiderivative e to the u. The antiderivative e to the u is still e to the u divided by two other terms, which would be Lenny and 1. So the fact that it's the natural log of e and 1, I'll have 1/3 of e to the u by itself plus the constant c. That's the 1/3 distributed into these two terms. So my final answer is 1/3 e to the x cubed plus c. William?
Do I have to write it's divided by L and E times 1? Because
Nope.
So that 1/3 in front takes care of any sort of chain rule that would happen?
Yes.
Okay.
Yes. This is the way you'll never forget the chain rule. Yeah.
So when either taking the derivative or antiderivative of an exponential x, you're either taking the derivative and multiplying it or taking the derivative and dividing it, right? So to find the derivative, or to find the antiderivative, you have to take the derivative and divide it.
All right. If I were to pre-write this, again, I'm going to have multiple different, okay, I'm going to have cotangent to a 1/3, and I'm going to have cosecant to a square. And so choosing between these two trig terms, which one do you pick? Okay, well, powers aside, no, not looking at the powers at all, like cotangent and cosecant, you gotta think about who is the derivative of the other. Okay, cotangent, who's cotangent's derivative? Cosecant squared. Cosecant, what's its derivative? Both a cosecant and a cotangent. So I want the one that its entire derivative is represented here. So I'm going to choose cotangent as my u. Cotangent of x.
Sorry, why cotangent? Because its derivative will be.
Cotangent's derivative is cosecant squared of x. Cosecant's derivative requires both an extra cosecant and a cotangent. So right now I'm looking at, I've got cotangent and I've got cosecant squared. I have its whole derivative. If I do the cosecant and I go the other way, I don't have its entire derivative. As part of it, I have cotangent present, but I don't have the whole thing. All right, so my derivative here, derivative is cosecant squared of x, and the derivative would be du over dx. So then dx by itself is 1 over cosecant squared of x times du. So moving the 1 over and getting dx by itself. So what I am replacing here is what I chose for my u and my dx. For now, I'm trusting the process and I'm entirely ignoring cosecant squared x, but I'm going to trust the process. So I'll have that turns into u. I'm trusting that something will take care of cosecant x squared, and then I'm going to replace in 1 over cosecant squared of x du. So again, my trust in the process is rewarded because the cosecant squared and the cosecant quantity squared and the cosecant squared of x are the same thing, so they reduce each other perfectly. So all I'm left with is just u to the 1/3 du. That was it. So the antiderivative of that is u to the 2/3. U to the 4/3 times 3/4 plus the constant c, which I can change back to cotangent of x to the 4/3 plus c. Yeah.
Is the derivative of cotangent, isn't it negative cosecant?
Oh, man. Yes.
I don't want to.
Yes. Yes. Yeah.
If we leave it in terms of u, is that bad?
Right. So that would, you would not get full credit if you leave it in terms of u. It needs to be returned back to its x. But if it was a multiple choice, they would basically force you to do that, right? All right, last one. A trig substitution might be helpful as well, okay? Because I said a couple things we were looking for. We're looking for parentheses. We are looking for products. And what's the last thing? Quotients. We're looking for parentheses, products, and quotients. So a trig substitution might be helpful because here we don't have any parentheses and we don't have any products, but we do have a quotient. What's the quotient? Yes, that I can change this into cosine over sine. So I do have a quotient. In a quotient, if you get one, the u is always the denominator. Okay? The u is always the denominator if you get a quotient. So sine of x is going to be chosen for our u, which is awesome because then cosine of x is my du dx. So du is 1 over the cosine of x. Sorry, dx is, there we go. So when you go back to, when you're done with your pre-work, you are changing the denominator only and the dx only. Don't touch your numerator. Trust the process. So I will have the cosine of x over a denominator of u times 1 over the cosine of x times the differential of u. See how clean that turns out to be? Which means all I'm left with is 1 over u times the differential of u, which has a beautiful antiderivative. The antiderivative here, if you rewrote u, it would be u to the negative 1, wouldn't it? Okay. The regular rules of u to the negative 1 would be when you add 1, you get 0, and then divide by 0. This is the only time that you're going to use an ln. Ln is the only thing that protects you from dividing by 0. Some of you on your test used ln multiple times. You used ln in inappropriate situations for every denominator. You only use it for denominators that you would be protected from dividing by 0. So this is an opportunity for me with my absolute values to remember my u. Okay, plus c. So our final answer then is the natural log of the absolute value of sine plus c. So there were some of you last chapter that were asking what the antiderivative of cotangent was if it had a perfect, and I said, yes, it does, we just don't know it yet. The perfect antiderivative of cotangent is the natural log of the absolute value of sine. All right, that's it.